Hello everyone. So today we will discuss about the DC biasing of the BJT circuit. So you see here, this is an NPN transistor and this is the internal structure of the NPN transistor with its terminal, base, collector and emitter. So first, before going to the biasing circuit, first we will discuss about the input output characteristics of the BJT circuit. So here in the input characteristics, we vary the input voltage VBE and we observe the input current IB, keeping output voltage to be constant, say for example 5 volt. So the input characteristics will be something like this, which is similar to that of the diode characteristics PN junction, because we are giving the input to the base terminal and observing the base current corresponding to the base current. So this will be the input current and this is the minimum voltage, which is the threshold voltage to turn on the device. And for the output characteristics, we vary the output voltage and we observe the output current, keeping the input voltage to be constant, somewhere little greater than threshold voltage. That is the minimum voltage what we keep here. And when you vary the output voltage, the output current will be something like this. Initially it will vary according to the output current will vary according to your input output voltage itself, VCE. We vary the VCE and we observe the output current IC. So in the input characteristics we observe the input current IB. So here in the output characteristics you see, so the initially this region is called as saturation region for the BJT and this region is called as linear region for the BJT. So here for the device, the transistor to act as an amplifier, it should be in a linear region. That means it should be in a constant current region. And the value corresponding to this point, this Q point, is called as ICQ and the voltage corresponding to this point is called as VCEQ. So this is the Q point what we have to achieve before we start use this device to work as an amplifier. And other than this, certain relationship between input current and output current you should be familiar with. We know that the output current IC will be beta times of input current IB, where beta is the current amplification factor, or it is also called as current gain of the amplifier. Okay, and your emitter current IE will be IB plus IC. That will be your IE. It will be IC plus IB. Since IC is beta times of IB, so IE will be beta plus 1 times of IB. So since beta is very large compared to 1, you can approximate this as beta times of IB, which is same as your IC. So the current IC and IE are almost same, right? And now coming to the biasing of the circuit, there are three types of biasing. One is fixed bias, the second is emitter bias, and the third is voltage divider bias. So these are the three types of biasing circuits. So first we will start with the fixed bias. Fixed bias circuit. So we will take it a simple fixed bias circuit, which is for NPN transistor again. This is RC, this is RB, and this is VCC, and the emitter is common for both input and output. So this is how you give the input V in and you take the output V out. Okay, so this capacitor is used for the AC analysis. Since we are discussing about the DC analysis, we neglect this capacitor because it blocks the DC component. Okay, so now to find out the bias point, basically bias point means VCEQ and ICQ. So to find that, we will apply KVL to input loop. KVL to input loop. I will redraw the circuit for simplification. This is emitter, this is base, and this is collector. So only RB will come to the input loop. This is VCC, right? So, and this is IB is the current which is flowing through that. So applying KVL to the input loop, the equation will be VCC is equal to IBRB plus this branch VBE. Okay, so we are supposed to find IB. So IB is VCC minus VBE divided by RB. This is your IB. Okay, so using this you can find out what is IC, which is nothing but beta times of IB, which is nothing but your ICQ, right? So this is how you find the output current ICQ. Similarly, to find the output bias voltage VCEQ, we will apply KVL to output loop. So I will redraw the circuit for only output loop. VCC, this is RC, and this is VCE, right? So this is base which will not come to the output loop. Only the collector and emitter will come into the output loop. So applying KVL for this loop, the current flowing through the RC is IC. So it is VCC is equal to ICRC plus VC. So your VCEQ will be VCC minus ICRC. So this is how you find the output bias voltage. Taking an example, numerical example for this circuit, taking RB as, say for example 240 kilo ohms and RC as 2.2 kilo ohms, and taking beta value as 75, you can find out what is the bias point, that is ICQ and VCEQ for this circuit with a numerical value. Okay, so VCC you take it as 12 volt. So you will get IB, which is 12 minus 0.7. 0.7 is nothing but VBE. So this VBE is the nothing but the voltage across base to emitter, which is minimum voltage across this PN junction. Okay, so which is 0.7, and RB is 240 kilo ohm, and solving this you will get approximately 47 microamps, and substituting this for ICQ, which is beta times of IB, 75 into 47 micro, you will get approximately some 3.2 milliamps. Okay, and similarly for your VCEQ will be 12 minus 3.2 milli into 2.2 K So VCEQ will be around 4.3 volts. So this is the bias point, output bias point for the circuit using fixed bias technique. So you can also make use of other types of biasing circuit, which you can take it as, on to the next. So the second one, which is emitter bias. Emitter bias. So I will modify the same circuit for emitter bias. So emitter bias means you will be having an additional resistance Re, that is emitter resistance. Okay, and this is Rb, and this is Rc, and this is VCC. So this is the same common emitter configuration with emitter bias, right? So now to find the bias point, that is ICQ and VCEQ for this circuit, what we will do, we will apply KVL to input loop. So I will redraw the circuit for the input purpose, neglecting the capacitance. So this is the modified circuit for only input loop. This is VCC, this is RB, you have VBE in the loop and RE, the current flowing this through this is IE. So applying KVL for this loop, you will get VCC is equal to IBRB plus VBE plus IERE. Okay, so substituting this IE in terms of IB, you will get it is 1 plus beta times of IB into RE. So finding out the expression for IB, it is VCC minus VBE divided by RB plus 1 plus beta times of RE. This is the expression for IB. Okay, and IC will be beta times of IB. So this is the ICQ for the emitter bias circuit. Similarly for VCEQ, we apply KVL to output loop, which I will redraw this. This is RC, RE. So this is VCC. The current through RC is IC and the current through RE is IE. And this is VCE. So the equation for output loop is VCC is equal to ICRC plus VCE plus IERE. Since IE can be approximated to IC, I can replace this IE as IC. So my VCE will be VCC minus IC into RC plus RE. So this is my expression for VCEQ. So taking the same numerical value for this, which is 12 volt VCC, RC is 2.2K, beta is 75 and RB is 240K, and I will take RE as some 1K. Okay, so now substituting this numerical for value to find IB, which is 12 minus 0.7 divided by RB 240K minus plus 1 plus beta times of RE, which is 1K. Okay, so you will get approximately IB to be around 35 microamps. This is your new IB, and IC corresponding to this will be beta times of IB, which is 75 into 35 micro. You will get ICQ as 2.68 milliamps. This is your ICQ. Similarly, for VCEQ, you will get 12 minus 2.68 milli into 2.2K plus 1K. You will get as 3.5 volt VCEQ. So by looking at this, both the type of biasing, okay, for the same numerical value, okay, so here you see we have fixed bias configuration. In the fixed bias configuration, what we have obtained the ICQ is 3.2 milliamp. Okay, so the ICQ is 3.2 milliamp and VCEQ is 4.3 milliamp. Whereas in the emitter bias circuit, what is the value? We have VCEQ as 3.5 volt and ICQ as 2.68 milliamps. So there is slight change in bias point. Okay, so this is how you get the different biasing conditions for the different types of biasing techniques. Okay, and in the next class we will discuss about voltage divider bias circuit.